Hello, today we'll learn how to calculate the equation of state of a graphene monolayer in order to obtain its optimal lattice parameter and equilibrium cell values. If you've ever done an EOS calculation manually, you already know the problem. You need to generate multiple strain structures, modify input files again and again, submit many separate calculations, collect the energies, and finally feed them to an equation of state. It's a repetitive, time-consuming cycle of generating strain structures, modifying input files, and manually feeding data, where a single small mistake can affect the final result. What we need here is a reliable, automated workflow that handles all those steps consistently. That's where ASAP comes in. ASAP automates structure generation, manages calculations, and performs the equation of state feeding automatically. The gain is simple: fewer EVOs, faster results, and workflow that scales to complex systems. Before diving into the setup, let me briefly mention why graphene. Graphene is a two-dimensional honeycomb lattice of carbon atoms. It has exceptional mechanical strength, very high carrier mobility, and tenable electronic properties. That's why it remains one of the most studied materials in condensed matter physics and nanotechnology. Now, let's get started with the workflow. In ASAP, create a new project and select the equation of state calculation type. Here, you can choose between Quantum Espresso or Siesta, depending on your preference. Now, we can define our strain parameters. For this example, we'll use the PVE exchange correlation function. Typical parameter values such as cutoff energy, smearing, and K-point mesh can be kept as default for this demonstration, although in a production calculation they should always be convergence tested. If we now go to the Select Parameters section, we can define our number of images, each one representing a slightly strained version of the structure. To get a good balance between precision and computational cost, we can use between 5 and 7 images. It's important to mention that for graphene, ASAP ensures the vacuum thickness remains fixed while varying the in-plane lattice parameter. Finally, in the Run tab, ASAP handles the distribution of calculations across your variable codes automatically. Press Run button, and once finished, click Exit and Analyze. Here we can see how ASAP provides the feed curve and directly outputs the equilibrium volume and optimal lattice parameter. Just like that, in just a few steps, we've replaced a repetitive manual workflow with a consistent automated process. This optimized configuration will serve as the starting point for further studies, such as functionalization or doping. That's the power of workflow automation. Please, if you like this video, subscribe and don't forget to use our free trial. Thank you.